Okay, hey everyone, Jordan again from Dimension Labs. So today we'll be talking about stable memory, stable structures, I guess safe upgrades and stuff like that. So I will share my screen. Okay, so again we'll go to the ASL book. Today we'll be covering chapter 12, which is all about stable structures, and then also I guess we'll discuss the chapter 16, the canister life cycle, and then we'll discuss the reference section also for stable memory. So first, let's see. First, we need to understand the two main areas where you can store state or data on the internet computer. And we did discuss this in other lectures, but the first location would be the heap. So if we have a very, very simple canister here, actually this would need to be an update function. So go back to one of our very first examples. Let's say you just have a simple key value store. Right. Okay. Let's say our database is just a string, right? If we, not a string, sorry, but an object, right? It's a very simple map, keys to values. So if I want to set these, and I would just have to type this. I could say that the keys are strings and the values are strings. Then put that onto the database. Yeah. Okay. So right here, this database, we're just setting a value into here. So we're going to fill this object up with key value pairs. This variable db, because it is a global variable, and according to how JavaScript interpreters work, things that are global like this are going to be stored on the heap. On the internet computer, the heap is 4 gigabytes in size. And something you need to understand is that when you deploy your canister again, or every time you deploy your canister, that heap is entirely wiped. So all of your global variables are going to be completely erased, and your new code or your new WASM binary is going to be, it's going to replace the old one. So you have new code, but you lose all of your variable state. And there are some interesting technical reasons why this is the case. It's just very difficult for you to guarantee that the data structures that you've created will, my understanding is that it's very difficult to guarantee that they're going to be, in exactly the same location, basically, or the exact same shape under the hood in memory. So if you don't wipe your heap, you might end up, this database variable might end up pointing to some other location in memory or something and causing, undefined or just, crazy behavior to happen. So because we have to, we basically wipe it. There's another place you can store data. It's on the stack of the function. So, every function does have local, I guess you could call it local storage for that function. So you could create variables inside of here. Let's say I wanted to move the database to be in here. I could do that. But of course, this variable will be, it will not exist basically or not be accessible to you after the function returns. So there's the stack as well. There's the heap. And I just want to point out again that, a key difference between the internet computer and other blockchains in capabilities is that these compute resources, the heap, the stack, and then the next location I'll talk about called stable memory. I think generally you're going to find that they're orders of magnitude bigger, right? Like up to maybe 1,000-ish times bigger. So that's pretty cool. So it does seem pretty undesirable to have your heap wiped because your heap might have valuable information in it. And so to deal with that, there's a special storage location in the internet computer called stable memory. Stable memory is like the heap in that it is, a general purpose place to allocate your memory, but it's treated differently than the heap, and it is actually persisted across your canister deploys or your canister upgrades.
Excuse me,
Now,
Jordan. Can
yeah.
you make a little bit bigger?
Oh yeah. Sorry, I thought I had already zoomed.
Perfect.
So the stable memory is persisted. The heap is not persisted. Now you might be wondering if the heap and stable memory are just general purpose data storage locations. Well, what makes stable memory different than the heap? And what makes stable memory different is it's not really that the stable memory is that different, but it's what you have to do to the memory. You have to serialize your data structures into basically raw bytes, and then you have to deserialize them after you upgrade and restore your data structures. That's the main purpose. And that is going to get around the problem of the data structures possibly, the internal shape and memory structure of them changing every time you compile a new binary. That's how we get around it. We basically take this database and we serialize into some format, store it in the special memory location, and then after the upgrade, we get it out. Now, I want to just copy out what I'm about to show you with this. You probably don't want to do what I'm about to show you. You don't want to deal with stable memory directly. Stable memory is a very low-level API that just deals with bytes, basically. What I will show you after stable memory is stable structures or stable data structures. And it's the stable structures that provide you with nice, very close to native data structure capabilities. And moving forward, I feel that at least for Azel, for Kybra, and probably for Rust, that is going to be probably the best path forward. Motoko, actually, I think they are looking into building these stable structure capabilities into their native data structures. And they can do that because they completely own that compiler and they can change the language however they want. So just FYI. So to access the low-level stable memory API, by the way, you import the IC object. IC has a ton of capabilities for you. And what you can do is inside your pre-upgrade function, you can actually serialize what you need to serialize and store it in stable memory. So we'll just make a function called pre-upgrade. So it turns void, has no parameters. So we're going to serialize this and then just store it in the stable memory location. So how are you going to do that? One really easy way would be to just turn it into a JSON string. In practice, this will actually have some problems because you can't stringify big ints and stuff, so you'll have to do a couple things to truly make this work. And this is not the way that you want to do it, by the way. This is just for demonstration purposes. So now I have this JSON object. Then what you would need to do is stable 64, right? And deal with your offset. So I'm going to assume that there's nothing in stable memory right now. So the offset here is, basically at what index in the stable memory you want to write into. So notice you're going to have to deal with all of this. If I write from index 0 to index 1000, if I want to write something else, then I can't use any of those indices. So it's very, very low level, like I said. And then basically I would have to change the you'd have to do something to change this into bytes. You'd have to serialize it somehow. And there's a number of ways to do that. So just for demonstration purposes. Okay. Then what you would do is in post upgrade. So pre-upgrade runs right before your heap is wiped and your code is changed. And post upgrade runs after the heap is wiped and after the code is changed. So now what I could do is I could get the db.json bytes out. I would have to say like stable64 read. And again, you have an offset and a length. So I would say offset 0. And I would really have to store the length of these bytes somewhere, right? But let's just say we know it's 1,000. I'd read those, and then I would turn it, to JSON, pretend that API exists. You'd have to figure that out. And now it's back in JSON. And then I'd say, okay, set the DB to the DB.json. And then it would restore the data structure. So yeah, I left some details out. It's not exactly how you do it, but the point is that you need to serialize and store into stable memory during pre-upgrade, and then deserialize and deserialize back into your native data structure, and then write that back into the heap. So this is just not like very ideal, especially in Motoko. I know people have had lots of problems with deserialization and deserialization and hitting the threshold for instruction counts, like how much computation you can do inside of these methods, and running into like garbage collection and heap issues. It's just not super nice. So the Dfinity team created a really cool project. Let's see if I can find it for you. Called IC Stable Structures. If you want to take a look at this under the hood, it's all written in Rust. And they basically have a number of data structures that try to map to native data structures that you would find, like vector and B-tree map. The B-tree map is just it's basically like an object with key values, but it uses the B-tree. It is a B-tree under the hood to store the data, which gives you certain properties for searching. So in Azel, so you can use this in Rust just raw. I think Motoko does have a concept of stable structures now as well. I'm not sure the status of that. But in Azel, we have exposed the Rust the Rust stable B-tree map data structure we have exposed to you with a nice TypeScript or JavaScript API, so that you can just delete all this stuff and use stable B-tree map directly. So yeah, let's just let's make a user one. So this is basically going to be like a database table that stores users in it. Let's import record. ID, let's make our IDs I don't know, principals for now. And then have the username that's just string. So to create the stable B-tree map, you need to define the key type. In this case, we'll make the keys principals. And then you need to define the value type. In this case, we'll make the value a user. So keys will be principals, which are the IDs, and the values will be the users. And again, this is just under the hood. I mean, you can think of it as just an object. It will just have keys to values. Now, every stable B-tree map needs to be initialized with a memory ID. So if we look at the types for the constructor here, you need a memory ID that's a number, and you need a maximum key size and a maximum value size. The memory ID, every single B-tree map that you create needs to have a unique memory ID. This is going to be a number between 0 and 254. So you can only have up to 254 of these stable structures right now. And you cannot reuse these IDs. Once you create a stable structure with an ID, you're stuck like that stable structure is assigned to the ID. So in this case, we'll say 0. Then, this is also unfortunate, you need to decide how big these keys and values can be, like the maximum size. So for the principal, I believe that would be 31 bytes, and you can do some trial and error. If you make them too small and try to write into them, you'll receive an error in your terminal telling you basically the size. But just to keep it simple, let's just say a max size of 100 bytes for the principal. And for the user, well, we'll have 100 bytes here. I mean, you can think like how many bytes might you need for a username? Maybe 100 would be good. So maybe this whole thing is 200 with just the fields. And then you have to think about the actual record data structure itself. I don't know how big that would be, but again, maybe to keep it simple, let's just say it's 1,000. So you'll notice that that was a little bit complicated, right? Like the memory ID, it's just wouldn't it? It'd be ideal if you just had to do this and it worked, right? And you could just make these anytime, and you could just delete them and garbage collect them and stuff. That is just not the case at the moment with the underlying data structures themselves. Max keys and max values are currently a requirement. I know they are absolutely working to fix that, to get rid of these. Getting rid of the memory ID, I'm not sure. It seems super promising to get rid of that, but I mean, I guess they're trying their best to deal with the complexity of these data structures. So, and one thing that ASL doesn't let you, delete these stable tree maps. I think the underlying Rust actually does. So that's just something we would need to add in ASL. But yeah, that's the basic flow for, at a high level, figuring this out. Give each structure a unique ID, give each key a maximum size in bytes, and give each value a maximum size in bytes. Another thing to keep in mind is that these three things need to be static. They should not be variables. Don't say like max key size equals 100 and then put it in here. Don't expect to pass in the max key size. You need to statically define these maps. Okay, once you have a map though, what's awesome is, I mean, you just don't need this stuff here. So just delete that. And now, if we change pass again, not value user. Now, if we want to set something, we have a really nice API to work with. We just say users.insert, pass in the key, and pass in the value. There you go. Very simple. And insert returns an opt with the record. I believe the record, it'll be none if the record like already existed or something like that, and it'll be some if the record was inserted for the first time. So if you do want to store that your insert result, then you can have that there. And there's a number of other APIs that you have access to. So we'll just keep implementing this. In this case, it can actually be a query function. So we'll import that. For get, all we need is the key. In this case, we will return an opt user, right? And this is what's nice now that these compose really well together. So I'll return users.get key. And there you go. All type checks and everything. Yep, get returns and opt with whatever the value is. And there's another, number of other APIs you can do. Check if it's empty. You can get the items, so you can iterate over the items. Get the keys, get the length, get the memory ID. You can remove things. You can get just the values. Items would be keys and values. Yeah, so I mean, it's a very familiar API. And what's really cool is that under the hood, what's really happening here is that, for example, insert, it's basically at runtime in real time, it's serializing this value for you and storing it in stable memory. And it's doing all of the under the hood, reading and writing and offset stuff for you. So it's managing your memory for you dynamically so that you just have this beautiful, nice API exposed. So main point is you have a data structure that is a general purpose map. Put in your keys and values. I don't know if I mentioned, but the keys and values must be candid serializable. So all these types that you're importing from Azel, and if you need to learn more about candid, you can check out the candid chapter, right? Chapter 11, and you can watch the video that we did yesterday. These must be candid serializable. And then once you have it, you don't need pre-upgrade or post-upgrade, and you just use it like a normal data structure. If you want to go through a detailed, basically a tutorial on how to do stable structures besides this video, you can go to chapter 12. I did not mention, but stable memory right now gives you 64 gigabytes of storage. Now, if you're using stable structures, you're going to want to make these max key values as small as possible, because if they're too big, then you'll be wasting empty space, right? But 64 gigabytes is that theoretical maximum if you can fit everything in. And yeah, I think we basically talked about all these points. So yeah, you can go through this example. Every single API is shown for you here. And then there's also like a very simple application, like an audio recorder application where you do have users and then you have recordings. And yeah, here's the user type, here's the recording type. The audio is stored as a blob. We make them about 5 megabytes in size. And it just shows you how you create your users, read your users, delete things, create recordings, all that stuff. Some kind of crazy match stuff, but yeah. And then that's probably obsolete, but if you do want to create random, like truly random IDs, here's a nice, relatively simple way of doing that, using the randomness under the hood. And then what's really cool here is that it does go through how you can determine these max key and max value sizes by doing some trial and error. And yeah, I mean, there's some caveats to it. For example, don't use floats as keys or services or funcs, because under the hood, the ordering, there's no strict ordering on these, and so you might have difficulty. You might have just very, very inefficient searching through those data structures. And I mean, honestly, it's relatively simple. So if there are any questions, this is a great place to pause for questions. Otherwise, I can go over a few more things.
There are some questions. So there was a few, but I didn't want to interrupt. So is the canister heap persistent in a per request basis, or is it file cycle? To my understanding, in a desktop program, your heap lives until the program is closed. In a web app, is a per request cycle, or is it a heap per session? I think, yeah.
I think I understand what they're saying. So the internet computer, every canister, once you deploy it, it's an everlasting process. Like it is just going to sit and run until you shut it down or it runs out of cycles or the internet's supposed to shut it down or something like that, right? So it's just going to be running. So for every update call, if you change the state of your canister on the heap or in stable memory, it is persistent, like for the lifetime of that process, which means essentially indefinitely. There is no session built in. You could think of queries as a session in a way, because queries right? They're read-only. So all state every time. So a query can write into memory, right? So if I make a little quick database thing here, or just make a string. Right here, if I write something into the database, I'm writing to the heap. But because it's in a query method, the Internet Computer is going to discard all of those changes. So you could kind of think of queries as the per request memory, right? Anything you write will only last for the length of that request or that function call. But updates, those changes are permanent for the life of the process. Hopefully that
Yeah.
answers that question.
There was a question about the record. So could you explain what is a record in,
Records?
quickly? Yeah.
Yeah. So we had a whole video on Candid yesterday. You will want to review that video and you'll want to review chapter 11, Candid. A record, if you go here, is a record in ASL is going to be the same thing as a candid record, and a record is just basically a plain data object. It's your basic and main complex data type that lets you have key value pairs. So a record has a bunch of key value pairs, for example, right? ID, principal, username, string. At runtime, it will be an actual JavaScript object with those properties, and you can arbitrarily nest them as well. So it's like the same thing as like a JSON object or a JavaScript object, more or less.
Yeah. What happens if we don't use stable memory and we reach the limit of the heap?
What happens if you reach the limit of the heap?
Yes.
If you reach the limit of the heap, then you'll probably start running into lots of problems. Like if your heap is full and another update call comes in and tries to write into the heap, then I believe it will fail. Like there'll be some trap or something. And who knows, your canister might start slowing down. You might, yeah, there might be garbage collection issues, which the state of garbage collection on ASL right now is either unknown or not that great, though we'll be swapping out to a much better engine soon. So you don't want your heap to get used up, basically. But you have a lot of space to work with. So especially for this DAO project, I mean, depending on how many proposals you feel like your DAO is going to get, writing into the heap is probably the absolute easiest way to prototype and get started. And then if it's all working out and you prove the concept, maybe at that point you would consider using stable B-tree maps.
I also remember that there was some canister that got stuck. So there was one canister in production that the heap was very, very close to the limit. And essentially, when the canister was upgraded, there were some serialization happening, taking more place in the heap, and essentially the canister couldn't be upgraded anymore. So that's also one thing that can happen. But yeah, we are very far from that with the DAO project, at least for now. So next question, every time I update my canister, my data gets wiped unless I use stable variable. Is stable memory production ready at this point?
Stable memory is production ready on the Internet Computer, if that's what you're asking.
Yeah.
Yeah, stable memory at the protocol layer is production ready. The stable memory API here, like the low level API, I mean, it's very, very simple. So that's probably production ready. If you're asking about stable structures in ASL in particular, I mean, you have to go read the chapter, right? Like there are some caveats such as once you declare one, it you can't remove it, and then ASL's beta and all the reasons we talked about why you might want to consider ASL not production ready would apply to it. So you'd have to make that determination. I would not say like, I mean, ASL itself is not necessarily production ready. So
Yeah, I would say it's production ready for the bootcamp, but not outside of this bootcamp.
And it depends on on what you're doing. Like if you're making a blog or podcast platform or something, it's like you just need these
Yeah.
things to work. If you're making something that stores money, then maybe you don't store tons of money in ASL at this time.
Yeah, just common sense. What's the difference between the heap and the stable memory in terms of speed of input, write and read?
Um, in terms of scale,
Speed, sorry.
oh, speed, like, oh yeah, yeah, heap. Right now, heap will be faster. I don't know how much faster. Heap will be the absolute best you can get. But and I, this could have changed. Like I don't know if they've deployed this yet, but they are working to make stable memory uh, much better, maybe even as good as the heap under the hood. I don't know if they deployed that yet. So right now, it just depends on the state of this feature. By the way, if you guys have these types of questions about like under the hood performance and protocol stuff, the Dfinity forum, forum.dfinity.org, is absolutely fantastic for these types of things. So you might be able to go search and find out the exact status of that. But yeah, they're moving towards making it much closer to the.
Yeah, I think there was the same question about gas cycle consumption.
Yeah, I mean, the gas consumption will be like you will use more cycles with stable memory or stable structures than you would use right into the heap because it just inherently takes more. And I'm pretty sure they've mapped that under the hood.
I just checked, and the Wasm native stable memory is out there. I just posted
Oh,
the
it's live?
article in the comments. It's out there. So the performances should be pretty close. I think heap is still more performance, but yeah, it's starting to get very, very close.
Okay, nice. So yeah, it seems like they should be pretty performant, but ASOS will be less performant than what you get in Rust directly.
Yeah, also the article is very, very nice to explain what's happening when you write to stable memory and how it works under the hood. So feel free to check it out. We have another question. Is 64 gigabyte enough for event-driven Arch for production? I'm not sure I understand exactly, but yeah.
Uh, can I read that question? Is it in the Q&A?
It's in the Q&A,
Oh,
yes.
event-driven art. Well, I'm not. I don't see how the 64 gigabytes has anything to do with event-driven architecture. Maybe you could um, clarify your question. But the internet computer is, in some ways, you could consider event-driven already. So a video app. You mentioned video app. I mean, I guess so. Yeah, could you like store? I mean, it just depends on the needs of your application. So I know I'm not sure how successful the video streaming on the computer has been. There's been people prototyping with it, but I think there are some issues. So it just depends. Like 64 gigabytes is obviously not enough to compete with YouTube, but it might be enough for some other applications. So you'll probably need to stream together, hook together multiple canisters to store lots of audio or video, and then you'd have to figure out, streaming performance after that.
We've answered all the questions. So do you have more to the stable memory?
Oh yeah, I can dig in more. I really feel like we did cover a good chunk of it, most of the important stuff. I mean, chapter 12, build up in that for the tutorial. The canister lifecycle. If you do have some kind of need for serialization or deserialization, like your own custom, I don't know, thing, like maybe stable structures doesn't work for you and you want to write the stable memory directly, you can use, remember, pre-upgrade and post-upgrade. And then the stable memory API.
Are you sharing your screen?
Oh, sorry. I wasn't sharing my screen. Yeah, sorry, I was just showing you guys, again, chapter 12 for the tutorial, and then the canister lifecycle in chapter 16 I was showing you, right? Pre-upgrade and post-upgrade, just like we went through. It hopefully is obsolete with stable structures, like I said, but maybe you think of some reason why you need to serialize something or do something in pre-upgrade and in post-upgrade. And if you really do want to deal with stable memory under the hood, we didn't really go through the entire API, but here it is in the reference section. You can access all of these off of the IC object. So if you want to get, I guess, all the bytes that are in stable memory, you call stable bytes. If you want to grow the memory by a certain number of pages, like, look, this is really low-level stuff, right? Then you can grow it. If you want to read at a certain offset in length, you can do that. If you want to know what the current size is, you can do that. And then if you want to write, you can do that. And everything without the 64 is, I guess I'm not sure. I'm not sure under the hood what the layout is anymore, if they still have this like 4 or 8 gigabyte section. I think before they had like an 8 gigabyte section, and then they had a new section that was 64-bit that allowed you to have up to 64 gigabytes. So not sure why exactly you'd want to use this API, but if you want the full 64 gigabytes, then I recommend using the 64 version. So again, grow your pages, read at a certain offset, get the current size, and write. With these primitives, you can build abstractions such as stable structures, right? Stable structures itself is, I mean, there's nothing else it could use unless they gave themselves some privileged access to the protocol, but I'm pretty sure they're using the normal IC API that you have access to as well. So yeah, if you're a low-level person, go ahead and do these, but really it's all about stable structures. There are a ton of examples, right, in the examples directory. Remember, this examples directory in the repo has all kinds of examples for you. Yeah, I guess using stable structures in a variety of, some of them relatively simple, but audio recorder is relatively complicated. Stable structures will show you, a bunch of different things that you can do. And something really cool, maybe I'll point out, these keys, they can be basically any candidate type, right? So if you need to make like a compound key, technically you could make user the key. If you ever need compound keys where there are multiple things that are going into the key, not just one simple identifier, that's a way you could do it. That could solve some problems for you. And yeah, I think that's all I have for now.
Okay. Well, we don't have to do 1 hour if like you've covered everything. So yeah.
I think maybe we'll do one more exercise because I think this will be very useful to people. Let me actually go through how you determine the max key and value size. Because until they lift that, that'll be the absolute hardest thing to do with stable structures. So let me show you where you can read about this as well. Chapter 12. Yeah, just kind of near the bottom, I explain in here what I'm about to show you. So let's say you're trying to determine like, okay, what should the actual max key value sizes on here be? What I would recommend is starting with something ridiculously low, like 1, right? Now let's just clean this up. And then we will basically try to insert something, and then it should throw an error telling us what's wrong. Okay. Okay, so I'll just deploy this very simple stable structure. Remember, it has principals as keys and users as values. And the purpose of what we're doing is to determine what the max key size and the max value size actually should be. And we're going to do that by, obviously it's crazy that we even have to do this, right? And the way I'm going to show you is, it's kind of janky and weird, but I think it's quite effective. And I don't know of a better way really to do it. So we're going to call our canister, and we're going to call set. Okay, we're going to pass in just a fake principal. And then we're going to pass in a fake user. Okay. Perfect. So this is the error that you're looking for. Key is too large. Expected less than or equal to 1 bytes, because that's what it put in. Found 9 bytes. So that is on the key. So at least in this case, this is a 9-byte principal, right? But this is like a short principal. So I might want to see what a bigger, like maybe a canister ID would look like. And actually, I know that I think principals are a maximum 29 bytes. So sorry, I'm looking here. Let's just grab one of these longer ones and do it again. Remember, we're going for the maximum size that it could be. Okay, found 19 bytes. So 9 is probably too small. 19 is sounding more like it because, some principals might be a little, I mean, you could maybe go with 20, but I think I'm just me. I'll just go with 50. 50 is still really small. And I know that some principals can be up to like 29 bytes. And so this just allows some extra room just in case. Okay, now that I have that, so every time you change this, by the way, every time you change anything about a stable structure, I recommend starting your replica clean. It's going to write information to that stable memory, and you should treat your stable structures as immutable once you create them. So while you're prototyping, if you're changing anything about the structure, just wipe it clean and start over. Okay, so again, we'll do the same thing for user. And we know we want to be at least 50 bytes because if we think any principal could be up to 50 bytes, then this ID could be 50 bytes. And then we just need to think basically about the username and how big you want that to be. And I put in a username of lastmjs, which is a relatively short username. Okay, so my user is actually 39 bytes already. And we know that probably 19 of them, at least, are just from that. So depends probably on how big you want this. I mean, maybe you would want usernames that could be just as big as principals, more or less. So maybe a nice heuristic would just be to say 100. So there you go. I mean, that is just a simple way to start getting a feel for how big the key and value max sizes need to be. And then if we deploy and do this one more time, remember I cleaned the entire thing. And if we try to write our user and a principal, then it should work flawlessly because these are not big enough. Okay, it wrote, and I should be able to get it. But that's in this principle. There it is. Pretty cool. Okay, I think truly we have covered hopefully a sufficient amount. Uh, any more questions?
We do have some questions. So one question, we talk about heap being at maximum when the update arrives. Will it make sense by default on the IC protocol to reserve some memory or configure the canister to always use 90% of the 4 gigabytes?
To basically prevent you.
Yes.
Yeah, so to basically prevent your canister from reaching the limit, so it would give you some kind of warning back, right? Um, yeah, that could make sense. I wonder if let me just look. So, by the way, another really nice resource to answer these types of questions is here. It's called the Internet Computer Interface Specification. So this is a little bit more low level, but there is something called the canister status, and it has some information in it. It has settings. I'm trying to see if this is already something that exists. We have compute allocation and memory allocation. So you might look into the exact meanings of the memory allocation. I don't know if this is talking about the memory like per canister, how much of the total memory is allocated, or if it's like per subnet or something. So that might already be something that the protocol has. But yeah, I would recommend looking at the interface spec and looking at these canister settings and memory allocation. And you could search forum.definity.org to see if people have already talked about memory allocation.
One last question. What happens if I need to add a member to records during a canister upgrade using stable data structure? Can I use post upgrade?
So that's the problem. Once you create, yeah, that might be a case for using post upgrade because you would. I don't think you need to do it in post upgrade, but you would need to come up with some way to migrate your data. So right now, how stable structures work, at least with what I've implemented in ASIL and last thing new, there's not really migration support for your stable structure. So once you create the structure, you should consider it set in stone. If you want to migrate it, you would need to create a new structure, and then you'd need to write code that would read all of the records or whatever from your old structure, and then add the new stuff, and put that into the new structure with your type, if that makes sense. And you can try doing
One,
that in post upgrade, but I mean, when you're getting to large amounts of data, I just don't think that would you would probably run into the instruction limit. So you'd probably need to write uh, an update function or a series of functions that would do this one chunk at a time.
one thing is also when a canister is being upgraded, it's stopped, so there is no message coming. So if a user um, try to register to your application during the upgrade, the message will be processed after the upgrade. Uh, maybe that will also help the issue you mentioned. Do we have another question? No, looks like we're good.
Okay.
Well, thank you. Thanks you for the lecture.
Yep.
Next mentorship session, 2 hours, 3 hours, sorry. And recording will be on YouTube pretty soon. So have a good one, everyone. See you. Thanks.
See ya, guys. Adios.